this is an architectural design, not the architecture of the modular computer, just to be clear. So the talk today will be two part. The first part is me, and then I will hand over to Casper, a PhD student in our lab, which is more, I would say, hands-on graph problem. So I will try to give you an overview of what graph means for architectural design and in general spaces. So the talk is space as graphs. A little bit about me. So I actually got my PhD in the same building, 2015 on statistical signal processing, and then followed by a postdoc again, speech processing lab, and then moved to the computer vision lab, which is the other building, a small building next to ECHO. And then for a short time, less than a year, I was research in residence in Royal Library of the Netherlands, also working on computer vision algorithms. And since 2021, I'm an assistant professor and director, co-director of one of the AI labs, focusing on AI for architectural design. And that's why this talk is actually about the graphs and AI in architectural design. So the talk will be four parts. Yeah, I don't see it here actually, so I don't know where is the. I don't have them. Oh, okay.
You can go to more or that's fine.
Yes. So the plan for today is to talk about four maybe different but related things. The first part is spatial data representation. Second one is the visual place recognition task in computer vision. And third one is scene graphs and scene understanding. Fourth is floor plan analysis and synthesis. My background, as I just introduced myself, is in computer vision. So graph is actually not my natural way of thinking about the problem, but actually came out. So I heard something was a few days ago about having a graph problem, which means that you have a graph problem, but you don't know it's a graph problem. So I think I can be categorized as such, but then through, I would say, my research, we found out that in many cases, we actually, it's better to model your data and your processes as graph processing. So that's basically where the talk is also going. So we start with the spatial data representation, and I would start with this beautiful, I would say, map, which doesn't have to do anything with graph, but I think it shows how data representation and data visualization can bring in some hidden information to the world. So if we can imagine that we live in a 3D world, so we have our surroundings and our habitat is actually spatial, and we would like to model it computationally so we can analyze it efficiently, because no human can actually process things in this scale. So we would like to have good data representation which actually fits to the data that we have, so we can convert it into information that matters. So if you wonder, this is a map of the height of the canopies of the tree all over the world, and this is produced by Meta Sustainability, taking satellite images and running one of the most powerful image encoders on top of it to get this information with some other processing, and then they visualize it as such, where many researchers on earth science can actually extract meaningful information from the carbon storage and how to basically plan forests, etc. So I think this is a very beautiful but also very useful and powerful image to start with what data representation can actually do. I think maps perhaps are one of the most popular representation of a spatial data. A map is a structured representation of geography and topology, and then we see it in different scales, from let's say global scales to cities, to urban maps, to neighborhood, and to the building also as well, which is a building layout. So regardless of well, what is being presented in the map, because we can have different layers of information in the map, I think it gives us a very broad and overview of what matters for a certain task, which could be a navigation, which could be a planning, etc. This is a more graph-related example and data visualization. This is a road network in Los Angeles, and well, it's based on OpenStreetMap, which is a public and open source data. And using a Python package, you can basically visualize the roads whenever this information is available. So this is also in, I would say, in a city scale, how you can visualize or extract information and data, which is inherently topological, which makes it a good candidate for having a graph representation of it. And this brings me to a different scale, small scale. These are floor plan data you could see here in the image in the left. So the right part are actually images of building unit layout when they are color coded by the functionality of the rooms. So for example, kitchens, bedroom, bathroom, living room, etc. And to the left, you could see the graph representation of them. This is also generated by Casper, human generated. So you could see that how, again, these topological layouts on different scales, global, city, and building scale can be represented in terms of graph. And this is maybe the smallest unit that we know, but we can basically start from here and extend our popular world model based on this representation. Another example is this one from another PhD in our lab, Fatima, who is trying also to add surrounding buildings information to this representation. So given a floor plan, which is basically this one, looking at the surrounding and see what kind of environments is out there and what kind of environmental feature is actually important for the building, and trying to model that as a graph. So for example, you could see view to the greenery, maybe there is a noise source somewhere, view to another building, etc. That could be another node on the graph, which represents the floor plan building, and the edges could be the influence that they could have on the quality of living in that space. For example, if the bedroom is basically connected to a source noise, this is not a good thing, and it enables the analysis of floor plans in its context. And well, if you have it in larger scale, then you probably can learn from it how to design your buildings, which is actually environmentally sound. So that brings me to this slide, which is a bit romantic, but I would say it's sort of fits this talk, because I think one of the most important features of graphs are their flexibility. Basically, you could encode so many different heterogeneous data on nodes and edges where you can see this transformation. So given a space being a sort of a meaningless geometrical representation of our surrounding or our world, there are things on top of it which matters for designers and architects, and those are very different from environmental, let's say, aspects to, let's say, social values to user experience to comfort and all these things. And I would say these all can be represented by graph if you have a node and edge, and then you can basically represent all kind of data on top of it. This makes graph, I would say, a very good representation, which is very difficult, I would say, not natural to, for example, put it in pixels. If you have images of places, people and researchers have been trying to extract meaning from that, but it would be very difficult to really capture it in one, let's say, data modality. But I would say graph is a very flexible framework that enables that, and that's a good representation format for spaces or places. So we might be using this interchangeably, but you would know what I'm talking about. So that brings me to the second part of the talk, which is actually has been my focus, research focus during my postdoc time here, and that's visual place recognition. Um, Again, one of the most available, accessible, and popular way of capturing environment is actually image and specifically photos, because now we have all smartphones, then we can capture images. And one of the things that actually, as one of the inherent features of a photo of a scene, is actually where this has been taken, right? So this is a collection of my own phone photos, and you can probably already see some of the places that you might recognize, right? So what you're doing is that basically matching what you're seeing to your memory. And then you would know, for example, this was taken in Munich, this is London, yeah, Italy, Austria. So this is basically visual place recognition. That's we do it as a human in larger scale, as I saw, but also in a local scale. That's when we navigate through the rooms, buildings, etc. And this is basically the task of visual place recognition I wanted to talk about. I found a fun thing here. Maybe I'll try to. Uh, so there is no voice, but okay, let's just. So there are some nerds out there that they actually train themselves to find a place given an image. So there is a word cup for that actually. So you can see that given that image, it would do this, and then you see it's 11 kilometers difference between the guess and the actual location. So there is a ground truth for that image, and then they try to guess based on the visual features here. We don't have a sound here, but he's, for example, talking about the temple, the building, let's say, style, the people that are there, and then where this place could be. So the question now is, with visual place recognition, can we do this with computers? So can we train the computers to be smart enough to do the same thing? And what are the applications of visual place recognition, automated visual place recognition? The first one is long-term mapping, which is basically matching different views of different scenes within a city, so you can update the map regularly. Another one is indoor localization, which is very robotic. So if you have an agent, a robot agent, and then it performs a task in an environment, it must recognize, it must learn actually the map of that place. I think you could find it also in the vacuum cleaners that you can buy. Now, after a while, they can learn the map of and some of it is actually with the images. I think most recent ones actually using images the same as autonomous drivers. I think it was almost 4 or 5 years ago that Tesla actually announced that they removed other sensors for localization, and they only use images. So computer vision, that's also has an application on that. Again, in more industrial setting, agriculture, and places that people cannot go, actually mining, etc., so that they can recognize whether there has been, so the agent can recognize whether it has been in the same place before or not, and what's the relation between this scene and the other one. Again, with any kind of vehicle and security as well. So matching, I think this the scene cameras or videos that used for surveillance, and then see whether what is this place, etc. So that brings me to this slide, which is actually, again, an old work that I've done during my postdoc. And the result was this Amsterdam visual place recognition benchmark data set. What we did there, because to teach computers to be able to do this task is basically to give them pairs of images that look the same, or pairs of images of locations that look the same, and then they can learn the similarity between the images, right? So in this data set that we collected, we actually did that, but having in mind to have these pairs chosen very difficult, because we will see that some of the challenges with visual place recognition is that they can actually work in a same domain setting, meaning that the image has been taken with the same photos or in the same situation. But if there are a drastic shift between the two images, then they would fail. So what we did, actually, we looked at the City Archive of Amsterdam. They have a public data set of archival imagery from Amsterdam taken in the past 100 years, so since they had camera. And then we looked at the street view images to capture basically the same location as historical images. So this is a crowdsourcing. This was a crowdsourcing project when we had basically this platform, and we would pay annotators, basically, mostly Amsterdammers, to well, given that image, they can go to the map and find the current view of the of that location. And then we would check it, verify it, and this is a pair that the computer is going to learn from. So that's a benchmark that can be used for training and testing visual place recognition models. So, but what is actually doing? What's the task of visual place recognition? The task is that given a query image, so would be this one. This is one place. It goes to an image encoder, whatever. So, given an image foundation model, it can encode an image into a latent space, an embedding. The same thing, so we have a database to compare with. Let's say all the images in a database are geotagged, which means that we know the exact location of these images, like the map example in Amsterdam. So all the images there, street view images, are tagged, geotagged. And then we actually do the same thing with the database. So we pass them all through an image encoder. So here we have a query, which is a vector or matrix, but also the same for the database. And what we do, we actually rank all the embeddings in a database with respect to that query to find the most similar image. And once we have that, that's a match, and then we know the location of that image, so then we know the location of the query as well. Is it clear? Yeah. But what can go wrong, basically? So this, again, I think maybe it's difficult to. This is better. Shall I also do this? Okay. and you see the images better. So these are some examples from Amsterdam data set that we have. And for example, you could see occlusion, right? So maybe the image is taken in different situations. So you have an object which totally, well, destroys the pixel arrangement of the place. Different point of views, even removal of some objects, greenery, etc., which has been during because of the this long time lag. So appearance change is one of the most difficult things that appears in visual place recognition tasks in lighting, weather, shadows, seasons, vegetations, or structural changes. Um, in this case, we have a random setting, which means that all the gallery images are spread all over the map, so they don't have very close a structural relation. They are related in terms of whether this image is close to that one in a map. However, in the case of robot and agent, they actually move in a continuous path, so they would have a structural environment or a structured environment to exploit. So the question is, for such a mobile devices, you have a scalability issue. So what is the size of the database and how do you basically store and compare these images? Another problem is viewpoint change. Again, I showed you here, and perceptual aliasing, which means that in case of, again, indoor scenarios, for example, you have many staircases that they look the same, or the wall is basically the same. So there are many images in the database of the robot with camera that doesn't make sense. So you can find lots of matches if you do this image similarity. And so good news for you is that there are graph-based solutions for appearance change and scalability that can actually solve some of these problems. So I would say these are sort of inductive biases that we know about the structure of the database that is going to be searched. And then the graph-based solution is trying to take care of that. These are not my work, so I would be very careful in explaining what's best just for you as a placeholder. If you want to take a look, these are some of the works that are actually introducing these solutions. This one, I think it's from 2019, and it uses hidden Markov model based on the graph formulation. And so basically each image in the database is a node, and in the edge, basically based on the structure and the movement of the robot, you know that what's the probability of transition from this image to another one. So like predicting what would be the next scene, and basically they combine these to formulate the visual place recognition as sequence matching problem. So instead of one query, you get the sequence of the query and then it matches to that graph. So it's a subgraph matching problem. Another one which is actually also very popular, and there are so many works on it, but I chose this one because I think it was the first one that I introduced the co-visibility graph for a multi-view VPR, is also based on graph. So instead of having, so I showed you the Amsterdam galleries, there are random images, they are placed on a map. This time you actually create a graph of the database, and together with the images, then the matching is being done. And how it's being done is, so what's a co-visibility graph is that if you have consecutive images, or even not consecutive images, so imagine that I'm looking this way, and now I'm looking this way. So there are some features in the room that I can see in both scenes, right? So maybe this is the window, and this is a keyframe, or what they call it in computer vision is a landmark. So the window, and basically they create a graph if the window is in this image and in the next image and the other image. So then you have a graph, and the whole database is turned into a graph. And what they do then is that when This is very important for aliasing, for example. If you have a match between, again, the matching is done based on image embeddings, right? So if you have a vector of the query and then you match it with the embeddings of this database, you can compute a confidence level because it's only one image that has been retrieved, but the inductive bias that we have from the database knows that, well, if there's a match between this node and this image, it should be also some sort of high similarity score between the neighboring graph. So that's how they check or they add this how do you say, confidence score to the retrieval. And then maybe they have different candidates in the ranking, but the one that actually satisfies the neighboring nodes in a graph wins basically as the match for this visual place recognition task. Does it make sense? Or maybe the next one is actually better. So this is an example of a graph of the database, right? So you have a big database of images, right? Let's say you have an agent explores basically the whole building. It takes lots of images. So each of these node is an image, and it's connected based on the visibility of the objects or landmarks with another image, right? So for example, this is what is being presented in this cluster of nodes. And yeah, the same basically setting. So once you match one image with one of these nodes, then you want to check for the score whether it's co-visible in other nodes close enough to that graph. This is a hyperparameter, and there are also lots of researches being done. So how close, where to look, how to compute the score. So I would leave you the details. If you're interested, then please look at this original paper. And that brings me to the scene graph, the third part of the talk. So the whole thing is I'm trying to give you some sense of how graphs are related to computer vision, and specific these problems that I have been working with. So I'm sure that there are also lots of other problems, but this is not a complete list by any means. It's just the introduction of some of these applications in computer vision. And scene graphs are also very popular. I think there have been many papers, workshop tutorials recently in any computer vision conferences that I have been in. And what are these? So basically what it does is trying to explicitly model the structural relations between objects in an image. So for example, if I have an image and I pass it through one of, let's say, the state-of-the-art encoders, whatever it could be, CNN-based or transformer-based, they all have some sort of pooling layers, which destroys the structural information in the image. And yeah, some of the foundation models that we have now, they are so deep that they actually implicitly encode all the positional relationships between the objects in the last layer. So they actually have a good clue about where things are in an image, especially transformers, which are inherently using positional encodings because they're using these token systems within their structure. But then still, if the let's say the focus is in how different objects are appearing and interacting with each other in an image, scene graph has been proven to be way more effective, especially for visual language reasoning. So you might ask your favorite LLM model to create an image when the objects have a certain relationship. For example, create a circle within a square and then connect that to something else, when someone is holding it, all these interactions that you try to describe in an image for generative settings, these are better modeled by these scene graphs. Um, these are examples. This is I forgot to put an image credit for this. This is not my image. This is from Stanford, where you see that, for example, this is a man, and these are basically all the interactions that can have with another objects within this setting, like having it, wearing it, and then there are other objects, etc. So yeah, so many of different tasks are now actually using this kind of scene graph representation of an image instead of pixel representation of an image. This is also from Stanford. I'm trying to, this is one of the, this is a 3D scene, which means that instead of image, you have basically the structure in the image. This is an agent, let's say, moving through a space. It recognizes different objects using an inherent, let's say, segmentation model. Segment those and trying to find the relationship. Here's, for example, this is a glass bed. What kind of material? What size is that? Shape and affordance, for example. What can you do with the bed? Also, its relation to other objects which were detected here. So structurally, whether this is like in front, in the back. I also have seen the actual demo of it, I think last year, where they had a robot and then they queried, for example, on picking something from a scene. So there was this room, and what it does is it has this internal graph representation of that space that's been stored, right? So you want to deploy the agent in this environment, and then you do subgraph matching. So if you query, for example, you say, okay, I don't know, give me that bag on top of the coffee table, then it takes this as a text or natural language and transfer it into an text graph, and it matches that text graph with this representation here. And it actually, no, because all these things also are geo-tagged in its local coordinates. So it can find basically where the bag is, and it goes and brings you the bag. Very cool. So this is the 3D scene graph. And just to put things in perspective, these are two things that I've seen a lot in computer vision research: co-visibility graph and scene graph. And they're using graph, but they are also inherently different, because in scene graph, as we saw, basically what matters is the semantic information layer in relation to other semantic objects in the scene, and also their local locations there. So it's more about what is these things and what can you do with it. However, the co-visibility graph is really about where is this image, right? So where is this image and how is that connected really from a raw pixel or raw features to another image, so then we can understand how the database is made. They have different goals. I think co-visibility is more for localization and mapping, especially in more controlled area, like in a room or an environment that an agent would operate on. And scene graph is more for visual question and answering and more human-computer interaction, right? So then how can we convert basically what we see into a subgraph, and then we match it with what is being stored as a graph for a scene. Is it clear? Okay, and then that brings me to my favorite topic, which is basically on floor plans. That's what the research that we are doing now in the lab, mostly floor plan generation and search. So one of the, I think, very hot topics and interesting topics are floor plan generation. And this was actually, it was about 3 years ago or 2 years ago, we organized this workshop at in ICCV Paris. And this was the first computer vision aided architectural design workshop. And in there, we had this competition before the workshop where the data set was given basically for training a model for floor plan generation. And the task was that, well, the model needs to create this full floor plan, which means that it contains the room shapes and relation and looks like a floor plan, given basically the boundaries of the building or the unit, basically, and the graph. So this graph is a very natural way for architects to encode programs of a space into it. And this is something that is more, we thought it's more natural to be given by the designer than really being created by a machine. Because if you have a unconstrained, unconditioned generative floor plan model, it can generate anything. However, usually know what's the function of the building you want to design, and then also the boundaries, also the where you want to build this place is actually given. So we thought that it's a more natural way to formulate this problem. Therefore, that was the challenge. And later on, a year later, we published this paper as well, together with people actually won the competition on how to basically develop the models that can take graph as an input and generate this floor plans. Also, the data set made public, modified Swiss Sterling data set. It's based on publicly available data sets of buildings, but not in this format. We took it, and together with the people owning the dataset, we created a dataset that is machine learnable. So people can take the training part and then test it on a part of the dataset to generate these plans. One of the winning, let's say, people actually use this modified house diffusion, which is also sort of based on a graph representation of the geometry. Not exactly, maybe, but I would say it uses geometry sorted and relations in a way that can be represented in graph format. Yes, that brings me to maybe, yeah, this is almost done. Why we are doing this, and sort of a vision of except for the generation, what do we want to do with this graph representation of the floor plans? And that's the topological search engine, which are apparently very useful, I would say, tool for architects, special planners, and urbanists, because they're looking for within this topological space, and they would like to search within this space. However, most of the search engines are based on appearance retrieval. So if you ask your, I don't know, popular search engine like a Google Lens, for example, then you probably get most similarly looking floor plans than the ones that actually have the same topological structure. So that's why these kind of, I would say, graph matching problems. So that's all about graph matching problem, which Casper will talk about it after this, is very important. And one of the most important things also for search engines to be fast, right? So we don't have enough compute and time to do exhaustive search on this discrete non-Euclidean space of a graph. So this image also is created by Nano Banana, was very impressive, I would say. I just explained my idea of topological search engine and created, so I'm very happy with it. So the conclusion, I would say it's very useful actually to use these inductive biases that we have from topology and structure, even in the images, which are, well, themselves are structured set of pixels, but then more on different layers of information, let's say object relation, etc. So a structural modeling of images, especially when it comes to space, is very useful. Well, graph is a very versatile and flexible framework to model the built environment, and hopefully we can have these digital twins of our planet. So we start small scale. So if we can model the smallest unit, let's say floor plans, that's a built environment, or a tree in a forest, or imagine whatever, and then connect it through this graph extension, then we would have a very useful model to run different simulation prediction. And what is very popular these days are world models, so we can predict things, we can act open. And yes, so again, having graphs gives us a richer platform to add more semantics to the representation. It has been for a long time, this computational framework, a very, I would say, objective and a very solid way to model measurable features of the world. However, now with advanced graph processing, graph neural networks, graph convolutional neural networks, graph attentions, whatever, then we can basically add any kind of information on top of it, whether it could be edge and nodes containing videos, containing images, well, text, whatever. And given the tools that we have with graph processing, I think that's very valuable. Yes, so combining vision and I think graphs are also very powerful. This has been proven to be a very powerful way of approaching spatial intelligence. And yeah, we would like to also see whether we can leverage this to better search in a graph space. So that would bring me to this last slide, some extra references if you're interested on the topic, except for the ones that are in the slide. And I'm done.